In research described by lead author Greg Asner, scientists from the Carnegie Institution's Department of Global Ecology have revealed the first high-resolution maps of carbon locked up in tropical forest vegetation and emitted by land use practices. The maps integrate satellite mapping, airborne laser technology, and ground-based plot surveys. They pave the way for accurate monitoring of carbon storage and emissions for the United Nations Initiative on Reduced Emissions from Deforestation and Degradation. Programs like the RIDA initiative create financial incentives to reduce carbon emissions from deforestation and degradation, but they have been hindered by a lack of accurate, high-resolution methods to account for changes in carbon stored in vegetation. The study covered over 16,600 square miles of the Peruvian Amazon, an area about the size of Switzerland. The researchers used a four-step process. They mapped vegetation types and disturbance by satellite, developed maps of 3D vegetation structure using a light detection and ranging system from the fixed-wing Carnegie Airborne Observatory, converted the structural data into carbon density using a small network of field plots on the ground, and integrated the satellite and LiDAR data for high-resolution maps of stored and emitted carbon. The scientists combined historical deforestation and degradation data with 2009 carbon stock information to calculate emissions from 1999 through 2009 for the Madre de Dios region. The results showed that the total regional forest carbon storage was about 395 million metric tons, and emissions reached about 630,000 metric tons per year. Members of the Peruvian government participated throughout the research process to familiarize themselves with the new method, assess the method's advantages, evaluate deforestation and forest disturbance, and determine carbon stocks in an environmentally critical area of Madre de Dios, Peru. The study was conducted with colleagues from the World Wildlife Fund and in coordination with the Peruvian Ministry of the Environment. The scientists are expanding their demonstration and training efforts in the high-resolution mapping technique with the governments of Ecuador and Colombia. The research was supported by the Government of Norway, the Gordon and Betty Moore Foundation, the W.M. Keck Foundation, and William R. Hearst III. It is published in the September 6, 2010 early edition of the Proceedings of the National Academy of Sciences. This is John Strom for the Carnegie Institution. Wing Yang of the Carnegie Institution's Geophysical Laboratory is a co-author of research that for the first time allows scientists to watch nanoparticles grow from the earliest stages of their formation. Nanoparticles are the foundation of nanotechnology. It's been very difficult to watch these tiny particles be born and grow in the past because traditional techniques require that the sample be in a vacuum, and many nanoparticles are grown in a metal-conducting liquid. The breakthrough may allow researchers to control conditions under which nanoparticles are grown, which will affect a wide range of applications like solar cell technology and chemical and biological sensors. The scientists use high-energy X-rays and a fast area detector, the key components from the Advanced Photon Source, which is operated by the Argonne National Laboratory. It is the largest X-ray source of its kind in the United States. Atoms scatter the X-rays, producing a diffraction pattern that reveals the structure of the nanoparticles. This research is the first time-resolved study of the evolution of nanoparticles from the time they are born. Nanoparticles' performance depends on their structure, composition, and size. The ultimate goal of the research is to use these new techniques to track chemical reactions as they occur under a variety of conditions, and then use that knowledge to design and make new materials for energy applications. The research is published in the journal Nano Letters. This is John Strom for the Carnegie Institution. Julia Pongrantz of the Carnegie Institution's Department of Global Ecology is lead author of a new study on the impact of historical events on global climate. It's a common misconception that human impact on climate began with the large-scale burning of coal and oil in the industrial era. Humans started to influence the environment thousands of years ago by changing the vegetation cover of the earth when we cleared forests for agriculture. During high mortality events such as wars and plagues, large areas of croplands and pastures have been abandoned and forests have regrown, absorbing carbon dioxide from the atmosphere. On the other hand, clearing forests releases carbon dioxide into the atmosphere when the trees and other vegetation are burned or when they decay. The rise in atmospheric carbon dioxide resulting from deforestation is recognizable in ice cores from Greenland and the Antarctic that predate the fossil fuel era. The research used a global climate carbon cycle model to track how land use affected climate during 4 major events from 800 AD to the present. They are the Mongol invasions in Asia from 1200 to 1380, the Black Death in Europe from 1347 to 1400, the conquest of the Americas from 1519 to 1700, and the fall of the Ming Dynasty in China from 1600 to 1650. During the short events such as the Black Death and the Ming Dynasty collapse, the forest regrowth wasn't enough to overcome the emissions from decaying material in the soil. During the longer-lasting ones like the Mongol invasion and the conquest of the Americas, there was enough time for the forest to regrow and absorb significant amounts of carbon. The Mongol invasions had the biggest impact of the 4 events studied. Regrowth on depopulated lands stockpiled nearly 700 million tons of carbon absorbed from the atmosphere. This is equivalent to the world's total annual demand for gasoline today. Dwarfing each of these events, however, has been the historical trend towards increasing deforestation. Over centuries, this has released vast amounts of carbon dioxide into the atmosphere as crop and pasture lands expanded to feed growing human populations. The global impact of forest regrowth and even the long-lasting events was diminished by the continued clearing of forest elsewhere in the world. The study is relevant to today's climate issues by showing how land use choices can alter the global carbon cycle. Today, about a quarter of the net primary production on the Earth's land surface is used by humans in some way, mostly through agriculture. In the past, our impact on climate and the carbon cycle has been unintentional, but we are now in a position to make land use decisions that will diminish our impact on climate and the carbon cycle. The study is published in the January 20, 2011 online issue of the Holocene. This is John Strom for the Carnegie Institution.